So today we're going to try and master the cylindrical coordinate transform. What that means is we're going to have to translate between two coordinate systems, the Cartesian, which we're pretty familiar with, and the cylindrical, obviously. So let's go ahead and draw the Cartesian on top of this cylinder so we can translate between the two. I see so x direction, y direction, and z direction. Alright, so let's go ahead and change colors so we can think about our transformation. Alright, so typically we have some r distance, so I'll represent those three entries as this line right over here. And to break up the individual components, let's go ahead and relabel those. So the angle from x to y is phi. This is going to be our phi angle, and the angle from z to y is going to be our theta. Okay, so the main goal here is what is x, what is y, and what is z. First we need to figure out what this is right over here. I said it's some r, but what is that r? Do it in red. R is typically represented as x, y, z, right? Some x, some y, and then some z. And if we go ahead and project this one down into the xy plane, we can see here that the components of this projected vector are here and here. The components are a distance r multiplied by its projection on the x and its projection on the y. So this x is equal to r multiplied by its projection on the x, which is cosine of phi. Our y is equal to r times its projection on the y, which is sine phi. And if we recall that r is equal to the square root of x squared plus y squared, the equation of a circle in the xy plane, then we can see, since we're already creating the circle in the xy plane, and the only type of difference in the third dimension would be how high you are, we can just say that z is equal to z. Okay, so knowing this information, we can actually rewrite the unit vectors now, so we'll go ahead and start with r. R is going to be, we're looking at the projection of r, so right over here. It's going to have some x part and some y part, so it'll be x value in the x direction, derivative of r, plus y in the y direction, derivative of r. Then we're going to have a phi direction, so it's going to be x in the x direction, derivative of phi. Similarly, we have the y parts with the derivative of phi, and we previously said that z is just going to be the z direction. Alright, so plug in and derive. So plug this in here, plug this guy in here, and we have that r hat is going to be equal to derivative of r is pi dr is 1 and cosine is a constant, so we have cosine of phi in the x direction plus sine of phi in the y direction. Now let's go ahead and take a look at the partials with respect to phi. So plug this guy in here, plug this guy in here, and for the phi direction, it's going to be equal to sine is cosine and the derivative of cosine is minus sine. So we're going to have minus sine of phi in the x direction. Oh, don't forget the r, because we're not deriving with respect to r anymore, plus r cosine phi in the y direction. And the easiest one is just z is equal to the z direction. With the new unit vectors and what x, y, and z represent, we can go ahead and find a change in the infinitesimal volume. X is equal to r cosine of phi, y is equal to r sine of phi, and once again z is equal to z. Now in order to see what an infinitesimal change in volume would be, we're going to have to find the determinant of all of these. So we're going to have to take the derivative of all three of these with respect to all of the variables. So this is going to be dx dr by dr, dy by dr, dz by dr, similarly dx by d phi, dy by d phi, dz by d phi, dx by dz, dx by dz, sorry, dy, and dz by dz. Okay, what I typically like to do is rewrite two extra columns, just so I can do a pretty easy method of calculating. I'll show you guys what it is. So I'll rewrite the other ones in red. So dx, starting from this. And what the main idea is we're going to isolate the diagonal downs and the diagonal ups. So start over here. This could be our first diagonal down set. And our diagonal ups. And we're going to have to perform each of these derivatives. So for example here, we would do dx dr. So the derivative of this term with respect to r is cosine phi. And once you do all of these, you see that the tau is going to become r dr d phi dz. And what this means is when you're changing throughout the volume of the cylinder, you're going to have to apply this when you're performing certain calculations, like, for example, integrals. It's a way to translate between the Cartesian and the cylindrical axes when you're trying to perform analyses, like maybe through the surface of the cylinder or the entire volume itself. And then once again, like we said before, a change in the line element is going to be this. Okay, and just a summary for the cylindrical coordinate transform. Remember, x was our cosine of phi, y was our sine of phi, and z was just z. When we did the unit vectors, we said that r is equal to the change in r with respect to r, which came out to being cosine in the x direction, sine in the y direction, and 0 in the z direction. Phi dr, remember r is x plus y plus z. This is from our Cartesian, this is how we're transforming. So dr is by d phi minus r sine of phi, r cosine of phi, 0. And finally for the z direction, dz by dz is 0, 0, 1 biderivative. So, knowing this stuff, and knowing the line element, remember, dl, where h is equal to 1, so that's dr. Then the next coefficient is going to be r times d phi plus dz. From here we can figure out the area elements. The easiest way to do this is to see which one's constant. For example, if you have a changing phi and a changing z, then your dA element is going to consist of dl phi dl z, which is going to be this one and this one. So r d phi dz. Now for phi constant, we're going to have dlr dlz. So phi is constant, we don't worry about that one. dr dz, and if we have z constant, then we don't worry about the last one. And dlr times dl phi is r dr d phi. So these are our area elements. This is our line element. These are our transformations, where we took the partial derivatives in order to get the transformations. And these are just our explicit statements of what x, y, and z are in the cylindrical coordinate system.